The next speaker is Sidney Wilkerson-Hill, who's an assistant professor at the University of North Carolina, Chapel Hill. So Sid has also had the misfortune of having two big contacts with the center. He did his PhD with Richmond Sarpong at UC Berkeley. And then I was delighted that he joined our group to do a postdoc. And it was an amazing experience having Sid in the group, because he's definitely one of the most scholarly postdocs I've ever had a chance to interact with in terms of his depth of knowledge and his engagement in the literature. Very impressive indeed. So not surprisingly, he's doing really well at UNC Chapel Hill. We're delighted for how things are going, and we're really looking forward to hearing your talk. So the title is Synthetic Methods Inspired by Complex Natural Products. Welcome.
All right, thanks Hugh for the kind introduction. Let me go ahead and share screen. All right. It's awesome to be here. You know, I'm really excited to share with you some of the research that we're doing here at UNC. Hugh, thank you again for the intro and the invite. And I want to give a special thanks to Rio behind the scenes. Having been in the center and been in Hugh's lab, I know how demanding organizing these symposia can be, and also working out the technical difficulties. So thanks for that. You know, getting into the spirit of the center, when I was tasked to give this talk, I thought I'd share some reflections on my time in the CCHF. And when I reflect on, you know, what the CCHF meant to me, I can kind of think of three things. Three important things come to mind. One was great science. So when I joined the CCHF in 2015, it was a really exciting time for the center. You know, there had been impressive developments in these dirodium tetracarboxylate catalysts. And I was coming right off the heels of Hugh Davies showing that you could do site-selective CH functionalization with these dirodium tetracarboxylates back in 2014. And while I was in the center, I got to watch these catalysts evolve to some really impressive transformations. And you know, I got to say the center has afforded me some exciting opportunities. I would say one of them is being able to run a rhodium catalyzed cyclopropanation reaction on 50-gram scale. So here I have that kind of shown in my hood. And another is also being able to purify 10 to 20 grams of dirodium catalyst in a giant column while in Hugh's lab. And so for those of you that know the price of dirodium these days, that's a really tall task, and you have to be careful there. But while I have this picture up, I think one of the exciting things from the center and being in Hugh's lab too were the Hugh Davies stories. All right, and having this big column up here reminds me of one that comes to mind that I'm sure he's shared with many of you. Back in the day when he was first starting his company, he had to purify a large quantity of dirodium catalyst, and the column got clogged, so things started to crystallize out. So at the risk of losing all that dirodium catalyst, I think I recall Hugh saying he stuck a gigantic stick in the column to break up the solids and get the catalyst through. So that was one of the stories that sticks out to me, and it gives me a good laugh every time. So the second, I think, major feature of the center, the second takeaway message was great people, right? So here's a photo from the National Science Foundation site visit, and when the NSF was in Arlington, Virginia, back in 2017. And it was really a pleasure to have the opportunity to work with some of the best and brightest minds in CH functionalization. You can kind of see us all here together, gathered around a table, guided by our fearless leader, trying to solve all the world's problems surrounding CH functionalization. And the third thing that comes to mind when I think of the CCHF is actually ping pong challenges. So here I have a video of Hugh going head to head with Al Padua in a ping pong challenge. And so, you know, in addition to doing fantastic science and being around great people, everyone had a very laid back attitude. It was a cool place to be. It was a great time to be in the center. It was great people to be around. So Hugh is awesome at CH functionalization with these dirodium catalysts. He's also an extraordinaire in ping pong. But I gotta say, I think Al has given him a run for his money here, but that's okay. All right. So when tasked to give this talk, I was doing some reflecting about why we're doing what we're doing here at UNC. And I think, Allison, I reflect those sentiments that we're really trying to go after grand challenges. And this speech, or this excerpt from the moon speech given by JFK in 1962 really sticks out, and kind of signifies or underlines this idea of doing hard things, right? And so around that time, we were all trying to rally the troops, so to speak, to go to the moon. And a lot of people were really questioning, why do we want to do this? Why do we want to spend all of this money on fundamental research and put a person on the moon? And I think our president at the time summed that up very well. We want to do these things because they're hard, because doing hard things serves to measure and organize the best of our skills and energies. And that's kind of the philosophy on why I choose to do research and why I get excited about science. And it honestly directs a lot of the problems we try to tackle in the group here at UNC. And so really our mission is to go boldly where no one has gone before, for lack of a better word. We are really excited about exploring chemical space. And we believe that physically exploring chemical space will lead to developments and new developments in medicine. And I'd like to point your attention to this really, these exciting articles that were published by Jean-Louis Ramon back in 2012 and 2015, kind of outlining this problem, enumerating all the potential hypothetical compounds that you can conceive that comprise chemical space, all right? And I kind of make the analogy, like these computations are analogous to a satellite. You're surveying the wide variety of the universe, the chemical universe that's out there. But we really want to be in the spaceship. We actually want to go and make molecules and see what they do. And one of the, I think, interesting aspects that came out of this, this study was that approximately 99.9% of all molecules that could be conceived of have not been synthesized. And so there's a really great need to go out and make molecules. And I think, again, Allison really hit a home run there, kind of outlining that problem earlier in the day today. All right. And so how do you know where to go in space, right? What galaxy do you want to investigate? And so my philosophy on target selection can really be summarized on this slide. We're really interested in molecular complexity, which can be broken down into both synthetic and structural complexity. This kind of comprises this XY plane, but also we are really interested in accessing molecules that have function. So developing new reactions to access complex molecules that actually do something important. All right, to this end, some of the targets we are excited about here at UNC can be shown on this slide. And I've highlighted this cyclopropane unit shown in red because that, having worked in the center on rhodium carbines, these the intermediates are capable of doing some fascinating CH functionalization reactions, but historically, there's also done really phenomenal cyclopropanation reactions as well. But I would argue if you're trying to access some of these natural products, using the state of the art in cyclopropanation chemistry, using carbene transfer catalysis, there are some limitations, right? And so what we do is we term these types of compounds that contain these specific cyclopropenes found in nature as orphan cyclopropenes, because if you really go and scour the literature for ways to make these, there are no known catalytic enantioselective methods for their synthesis. And that really stems from the two ways we think about making strain 3-membered rings. One being a concerted 2+1 cycloaddition reaction, where you have some type of metal stabilizing a carbene unit. For these types of natural products, that would require the transfer of like dialkyl carbenes, and that has not been demonstrated yet. All right. And the other transformation one can think about is actually doing some type of intramolecular cyclopropane functionalization. However, when you're working with complex molecules, this strategy, though very versatile, can be somewhat of a limitation because it requires pre-functionalization of your substrate. So it adds synthetic steps. And since we're really focused on the synthetic efficiency, this is, again, not very viable. All right, so how are we thinking about addressing this issue? All right, so in our laboratory at UNC, we think about developing methods, and they fall into 3 main categories. One, when we're developing reactions, we think of bio-inspired reactions. So Allison is doing a great job actually using the enzymes. We're not that sophisticated, but when our reactions look in the mirror, we hope that they see an enzyme, and we hope that they try to mimic what enzymes can do in the flask, right? We also take these family-centered approaches where, we think about constructing a cyclopropane, but also the remainder of the carbon skeleton in complex cyclopropane containing terpenes. And the reason why we do this is because by taking a family-centered approach, we can not only access the parent, but potential derivatives that have various levels of oxygenation around the periphery. And then the final type of projects that we have going on in the group at UNC are what I call chemotype-centric cyclopropanation reactions, where we're really interested in taking any carbene that we want and transferring it to any olefin, right, to give us cyclopropanes that are not known, so unknown chemical space. All right, so the story I'm going to tell you today are two stories that were originally bio-inspired reactions. And as you'll see through today's talk, we've kind of made some strides in that area, but sometimes as research will have it, we don't always accomplish what we were trying to do in the beginning, but that doesn't mean we've given up on the problem, all right? So the first story I'd like to tell you is how we were thinking about developing biomimetic cyclopropanation reactions and how we got into this area of frustrated Lewis acid-base pair catalysis. All right, and it really comes from thinking about the biosynthesis of pre-squalene pyrophosphate, this complex cyclopropane that's produced in nature, right? And we can, upon analysis of this biosynthetic pathway, what we find is two molecules of farnesyl pyrophosphate come together within the confines of the active site of an enzyme to give pre-squalene pyrophosphate. And the way this takes place is via ionization of this pyrophosphate group using some Lewis acid. All right, so magnesium 2+. This gives an allylic carbocation, and because enzymes are just absolutely amazing, they're able to actually, these terpene cyclases are able to actually place this carbocation in close proximity to a double bond. And what's proposed is actually the intermediacy of a protonated cyclopropane, all right, so a non-classical carbocation in nature. And this gets deprotonated to give the neutral compound. Right? And so when we saw this, we were really inspired by this mode of reactivity because nature has found a way to simultaneously use an acid and a base without the acid and the base neutralizing each other. So this reminded us of an ongoing field in organic chemistry right now called frustrated Lewis acid-base pair catalysis, where in essence, you can take Lewis acids and Lewis bases, and provided that they're sterically bulky, they won't neutralize each other in the flask. And what they can do is go off and activate other molecules. The prototypical example being the splitting of H2. And when we think of the molecules that are capable of doing this, these highly electron deficient boranes, such as tris-pentafluorphenylborane, which we'll call BCF for the rest of the talk, and combinations of sterically bulky amines are able to split H2. We can also have intramolecular FLPs where boron and phosphorus are in the same molecule. We can even have some really exotic molecules such as these triphosphanines, which also split H2 and serve as FLPs, right? And so I really want to drive this point home. We're all used to thinking about classical acid-base chemistry. It's when you take this vinegar and baking soda and you get a volcano. So we all learned this in the 3rd grade. And this, I think, has inspired a lot of us to be chemists back in the day, truthfully. But when we think of frustrated Lewis acid-base chemistry, I like to point you to this GIF that I found online, where essentially the acid molecules in red and the base molecules in blue are trying their hardest to neutralize each other, but they can't because of the steric environment. And so they can go off to activate other things. Okay, so there were two main reports that served as inspiration for our study when we started our group here at UNC. One was by Douglas Steffen, who showed in 2007 that you can take BCF and tritert-butylphosphine and split H2 to get this borohydride and this phosphonium salt. And this stood out to us because it demonstrated the transition metal-like reactivity of organic compounds. When we look at the work of Guy Bertrand, which also came out that year, he was able to show that you could take these aminocarbenes and split H2. And this, again, was exciting to us because it demonstrated the relationship between carbenes and FLPs, all right? And so I think most of you can see where we're going with this. Transition metal catalysts, frustrated Lewis acid-base pairs, and carbenes all split H2, right? And so we can kind of put them on this diagram, if you will. And what they all have in common is empty orbitals and Lewis basic sites. Granted, in a transition metal, they're on the same atom. In a carbene, they're on the same atom, but frustrated Lewis acid-base pairs also kind of, in some way, fulfill this orbital analogy. The relationship between transition metals and carbenes is well studied, whereas the relationship between transition metals and frustrated Lewis acid-base pairs, or mimicking that reactivity, is much less underdeveloped. But when we started at this interface. We were really curious, could we develop reactions or where we could use a FLP to catalyze a cyclopropanation reaction, right? And so we took the simplest question possible. We asked ourselves, can we activate a diazo compounds without transition metals catalytically, all right? And so our first steps in this direction were aimed at kind of understanding the Lewis acid component of these reactions. So we left the Lewis base out. So it's not quite a FLP reaction yet, but that's our ultimate goal. And this work was done exclusively by one of my first graduate students, Joey Mancinelli. And I should mention this work was published last year in 2020. All right, so I'm not going to go through all the optimization that we did to try to get this reaction to work, nor am I going to go through all the substrates that we've kind of shown that work in these reactions, because this is published work. But the takeaway message from these studies is that you can indeed take these aryl diazoacetates in the presence of 10 mol% tris pentafluorophenylborane and catalyze a cyclopropanation reaction. And we believe that this proceeds through this Lewis acid activated carbene. Now, this is very much in contrast to the traditional way we think of activating diazo compounds. So transition metals such as dirodium is very well established to coordinate to the Lewis basic carbon atom of these diazo compounds, and then you extrude into through some back bonding event. However, what we're showing is we can indeed activate diazo compounds by coordination on oxygen, giving via this alkene diazonium intermediate that loses into. I should mention, as we were submitting our publication, there was a related report by the Milan group out at Cardiff that came out that year, showing the same reactivity, however, on mainly heterocyclic substrates. All right, probably the most exciting aspect of the study that kind of fell out of our foray into FLP catalysis, if you will, were the following schemes from this paper, and these seem somewhat boring on the surface, if you will, but we were pretty excited because when we take trans beta methylstyrene and we do the cyclopropanation reaction, we exclusively obtain this trans cyclopropane product. However, when we move to the cis isomer, we can obtain the cis cyclopropane product. So what that suggests is this reaction is both stereospecific and stereoselective, and it kind of rules out a carbocation or carbocationic pathway, which we kind of considered in the beginning. All right. And so one can draw a catalytic cycle to explain how this reaction works. We believe BCF coordinates to this diazo compound, giving an alkene diazonium ion that then loses into to give this Lewis acid activated carbene. So we don't call this a vinyl cation because overall this species is neutral. So it doesn't really make sense to call it cation. But this will then undergo a concerted 2+1 cycloaddition reaction to give cyclopropane products. Okay, so where are we going with this? So, as I mentioned, these are kind of our first steps into FLP catalysis, and we're really excited about developing other types of reactions where we have this Lewis basic component within the reaction, and so those studies are ongoing. But our logic for studying this reactivity is we really wanted to start with relatively simple transformations, such as these cyclopropanation of diazo compounds, and move to more complex and elaborate cyclopropane forming reactions without diazo compounds. So one can envision using the FLP concept to maybe access non-classical carbocations in this fashion, or using or intercepting protonated cyclopropanes in a similar manner that nature does. Okay, so switching gears a little bit, I want to talk about how we developed these halomucononitriles and what they have to do with cyclopropanes, if anything. All right, and it really comes back to, again, thinking about how nature makes cyclopropane. So I have this natural product curasin A on the slide, and it's known that the cyclopropane in this molecule is actually formed through this, enoate bound to an acyl carrier protein. So these can be reduced with NADH, giving an enolate ion, which will then essentially do an SN2 type substitution to give a cyclopropane. All right, and so when we looked at this, we squinted our eyes and we saw that this intermediate maybe could be related to ketenes. And so we became really excited initially about the relationship between ketenes and cyclopropanes. Now, these studies are still ongoing and it didn't quite pan out the way we wanted to. And unfortunately, I don't, for the sake of time, have time to go through how we got to these halomucononitrile reagents. But I wanted to point out that they were indeed related to this thought process of maybe using ketenes to make cyclopropanes. All right. And to that end, we found some really interesting and exciting reactivity of these compounds. these halomucononitriles are understudied reagents. Truthfully, there were no reactions known with these at the time that we started to study them. But what we found is they will indeed accept nucleophiles such as malanates or secondary amines, and we can do what we call programmed sequential addition reactions. So depending on the nucleophile, you can get the nucleophiles to add twice, or you can get them to add once, or you can add one and then intercept the chloroacrylonitrile intermediate with a different nucleophile. And what this has allowed us to do is actually access really intricate polycyclic scaffolds in a controlled manner. All right, and so this work was primarily done by another one of my first years, Adam Zahara, and our first postdoc in the lab, Elsa Hines, who is now transitioning out of the lab to start her independent career at St. Mary's. And so in our initial report, which was published last year, we found that we can add secondary amines into these halogenated mucononitriles. These proceed in really great yields. We can also add malanates into these, but what was not shown in our initial report is we can actually add beta-keto ester compounds as well. And these compounds, when you use these prochiral enolates, actually add in a way that is completely diastereoselective. So we obtain exclusively the C2 symmetric double addition adduct when we use these types of beta-keto ester derivatives. And that's kind of borne out through these X-ray crystallographic studies. All right, so what can we do with these compounds? And so Allison has showed some really nice biocatalytic approaches to these molecules, such as called bis-isomahinine and bismahinine, where one can think about forging this CC bond between these hydroxycarbazole units through an oxidation reaction, right? We were interested in a very different strategy to access these natural products where essentially this butadiene portion would arise from essentially this linchpin reagent that we've developed in our laboratory. So to this end, this, on model systems works okay. We can take gramine and in a single step, in two-step, one-pot operation, we can elaborate that very quickly to these indole malanates. And so we call these truncated monomers because as we don't have to actually make the full hydroxycarbazole unit to now add them into biscan or bisban to arrive at a compound that has most of the carbons you would need to make this symmetrical homodimer, all right? This proceeds really well on a gram scale. To access these non-symmetrical homodimers, we envisioned, again, using this program sequential addition strategy to access these compounds. So we can take, again, our same indole now, one equivalent of this, react it with our linchpin reagent, and then simply add morpholine to the pot. That gives us this extended dienamine, and simply treating that with trifluoroacetic acid affects this intramolecular cyclization reaction with removal of this Bach group. And so we were pretty excited about these because it kind of set the stage for maybe thinking about different ways of making these molecules where one can come in and do some type of cycloaddition reaction to this aminoacrylonitrile unit to access things like bismahinine. And furthermore, we were excited about this because these indole malanates are extraordinarily easy to make. So again, they come from gramine, and we can bring up essentially 10, 20 grams of these types of reagents in 2 hours in our laboratory. All right, but we also recognize there might be other utility in these types of reagents, in that they are protected bis-ketenes. So as you would imagine, these bis-ketenes are pretty exotic and reactive functional groups, but they've actually received considerable attention in recent times. So the Newton group last year showed that you can take these 2,5-disyloxyfurans and use them as bis-ketene reagents to affect annulation reactions. However, when we're looking at our reagents, we recognize a different disconnection where potentially we can make some really interesting dimeric compounds simply by doing a double Diels-Alder reaction across a bis-ketene equivalent. And this was exciting to us because this strategy would be convergent, modular, and unexplored. So, by that I mean, we're not just limited theoretically to accessing symmetrical homodimers, but presumably we could also access non-symmetrical homodimers as well. If we could control the Diels-Alder reaction to stop once, we can maybe go back in with a different diene to perform a second Diels-Alder reaction. That would allow us access to a variety of polyketide natural products, many of which again are made by oxidative coupling reactions. But as you can see, these 1,4-dicarbonyl units are kind of hidden in these molecules and our bis-ketene, our protected bis-ketene reagents serve as a bench stable version of that functional group. Okay, so again, our hypothetical transformation we wanted to develop is kind of outlined here on this top part of the slide, where we wanted to take one diene and react it with another diene to give a Diels-Alder adduct, and then have that react with another equivalent of the starting diene to arrive at essentially a dimeric cyclohexene. All right, and obviously this has a number of challenges. One being we have to find a way to break conjugation in these diene substrates. I think the most obvious challenge is we have to control for obtaining the cross dimerization products instead of the homodimerization products. We know that cycloaddition reactions are very sensitive to the steric environment across the diene, and also stereochemistry. So how do we control it now? 8 contiguous stereocenters potentially formed in these molecules. All right, so our proposed transformation is, can we take some type of diene with our linchpin reagents and arrive at these cycloadducts? And indeed, that is the case. So taking bis-bromoacrylonitrile, we can react this with cyclopentadiene at 60 degrees and obtain an 80% yield on gram scale of these 2 diastereomers. The endo isomer we've characterized by X-ray crystallographic analysis. And if we take these isolated compounds now and react them with more cyclopentadiene, we can indeed effect a double Diels-Alder cycloaddition reaction, albeit in lower yield. And so that works pretty well, but it's a complex mixture of diastereomers at the moment. But that would be inconsequential if we could remove the stereocenter by hydrating this bromoacrylonitrile unit. All right, and we're working with another former center member from Jamal Musayev's group, Professor Brandon Haynes. He's at Westmont College now in California, and he's looking at these reactions computationally so we can understand the energetics of these cycloaddition reactions. All right, we're not just limited to cyclopentadiene. We can use other types of reactive dienes, such as these orthoxylylines, which are generated from benzocyclobutane reaction partners. And these proceed in pretty good yield across the board, although we notice now we're forming regioisomers in this process. And so presumably because of this bulky TIPS group, we get a mixture of regioisomers. But as you can see, we were able to rapidly build molecular complexity from these substrates. All right, but how far can we push this? All right, so we're looking at now less reactive dienes. We don't have aromatization to help us out in these Diels-Alder reactions. And so we had to turn to Lewis acids to help us out in these types of cycloaddition reactions. And what we found after extensive screening campaign is that BCF, tris-pentafluorophenylborane, is actually uniquely capable of activating our bis-ketene reagent to affect these cycloaddition reactions, right? And this is born out of bis-ketene's unique ability to coordinate to nitriles, and we actually have X-ray crystallographic evidence showing that this Lewis acid can coordinate to the nitrile groups in our linchpin reagent and thus activate it. Now, at the time, we are not sure as to whether the cycloaddition reaction is happening across this di-activated compound or a mono-activated compound, but we think that'll be borne out in time with mechanistic studies. All right, and just to wrap up here, first year in our laboratory, Isaiah Erker-Frank is kind of taking this project by the horns, so to speak. He's really excited about these cycloadducts. So he's shown we can do some pretty interesting reactions on these types of compounds. Treating the cycloadduct with base, for example, aromatizes this ring, and this aromatization is actually coupled with the loss of this vinyl bromide. So we can talk about how that works mechanistically offline later. He's also shown you can take these aromatized products and perform cycloaddition reactions on those, such as this azomethine ylide 3+2 reaction. And then finally, no project involving a protected ketene would be complete if you could not change that alpha bromoacrylonitrile unit to the corresponding carbonyl. So what Isaiah has found is actually using standard conditions such as sodium sulfide or concentrated sodium hydroxide, or they completely, as you would imagine, completely obliterate our starting materials. So we had to find a milder way to do this, and Isaiah actually identified photoredox catalysis as the solution to this. So we can take these model substrates actually in more complex substrates too, in the presence of iridium PPY3 and tempo as a trap, and arrive at these tempo trapped adducts. Okay. So, I think I've gone over on my time, but again, it's been really exciting to kind of share some of the projects we have going on in the Hill Lab here at UNC. The stories I've told you today were all inspired by bio-inspiration, if you will. So trying to get our reactions to mimic what enzymes do. But we're still interested in this idea of how do you obtain these orphan cyclopropanes? Can we develop other reactions to do that? And so keep an eye out. Soon we're going to submit our kind of first studies on this idea. It's a family-centered approach where we can actually take various aryl halides with a reagent we've developed in our lab and actually install a vinyl cyclopropane in a single step. And we think this will actually drastically simplify the synthesis of these molecules because this fragment is kind of hidden in all of these complex natural products. So with that, I have to thank the group, the team. They're a fantastic group of individuals to work with. They make me enjoy coming into work every day, even when things maybe seem, even when things may seem dark. So thank you, Dr. Elsa Hines, Adam, Joey, and Isaiah, who I kind of highlighted throughout the talk today. I'd like to thank the department for funding. I'd like to thank Hugh. Thank you for the invitation again. And I'd like to thank you all for your attention. And I'd be happy to take questions in the chat.
Well said, thanks. That's a wonderful talk. So if this is a good time to express your appreciation, which is good to see coming through. That's very nice. Yes, the only little problem I thought with the talk was all of the ping pong points you showed. I think Al Padua won. But I want to tell you that Al Padua is in this is an attendee at this meeting, and I'm sure he really enjoyed it. So that was great. Again, because of time, I would suggest if anyone has got any questions and comments regarding a very interesting way that Sid has got into these cyclopropanation and other possibilities, please join him in the chat and we can have a discussion going there.